Bienvenidos a una nueva edición de los seminarios internacionales de frontera de ciencia de materiales. Y hoy tenemos un tema extraordinariamente interesante. Nos van a hablar, nuestra ponente, de aleaciones ligeras para su aplicación en el transporte. En definitiva, lo que queremos es sistemas de protección que, además de aligerar peso, sean amigables con el medio ambiente. Con nosotros tenemos a Eva Bierspika, o something like this, excuse me, que viene del Departamento de Ingeniería Química y Materiales de la Universidad Complutense de Madrid. Eva consiguió su graduado en Ciencias Químicas en Cracovia, tampoco lo voy a decir bien, en la Universidad. Can you help me with the name of the university?
University.
Well, you can understand her better than me. Y ya su trabajo iba enfocado a temas relacionados como la electroquímica, sensores electroquímicos y nanoestructuras. Posteriormente, desde el 2017 y hasta ahora 2018, está disfrutando de una beca en la Universidad Complutense de Madrid dentro de un programa europeo como es el Clean Sky 2, que se incorpora dentro del Horizonte 2020. Hasta el momento es coautora de 7 artículos internacionales, 2 capítulos de libro y asimismo tiene ya más de 38 citas en estas revistas de índice de impacto alto. Sus líneas de trabajo y de investigación se centran obviamente en la ciencia de materiales, en el anodizado de aleaciones ligeras para su protección contra la corrosión mediante tratamientos electroquímicos y asimismo en anodizados nanoestructurados de óxidos, ¿vale?, y sus aplicaciones. Yo no os robo mucho más tiempo, os dejo con ella. Seguramente que vais a disfrutar mucho de esto porque es un tema realmente importante, reciente y que está muy en boga. Thank you very much for your collaboration in these seminars and your participation. I'm sure that everybody is going to enjoy very much with your dissertation. Thank you.
Thank you. Welcome everyone. It is an honor to be here today with you. As you know, my name is Ewa Wierzbicka. And today I'm going to talk about light alloys and their application in transport and how to provide them with good corrosion protection. More than 100 years ago, the first gasoline automobile was invented. At that time, no one could predict how this invention will improve our life. This year, more than 80 million of cars will be sold and more than 1,700 large commercial aircrafts will be produced. Nowadays, we also must face the consequences of this invention. First problem is that the demand of fossil fuels is still increasing, but the source of them are being extremely fast depleted. Moreover, the car exhaust emit the wide range of gases and solid matters, causing the global warming and harming the environment and human health. So what can we do about this? Before solar energy and hydrogen fuel will be able to replace the classic oil or gas, we can do something more simple. Reduce the mass of the vehicles by application of lighter materials. What will allow us to decrease the consumption of fossil fuels and also reduce the emission of carbon dioxide. Application of light alloys based on magnesium and aluminium are very promising because they have much lower density compared to steel. By application of the same volume of materials, we can save 75 or 65% of mass by application of magnesium and aluminium respectively. Both of them, magnesium and aluminium alloys, are already used in application in automotive industry. Every year, amount of those alloys used are increasing. Currently, it is even more than 50 kilos of magnesium per car. Aluminium alloys are used also widely in aircraft industry. Those are the parts composed of varied aluminium alloys. Some of models of Boeings are composed even in 80 or 70% from aluminium. But pure aluminium and magnesium don't show appropriate physico-chemical properties to be applied for big parts production. And because of that, a huge progress in metallurgy was necessary. Currently, there is a lot of option to modify the pure metal by some alloying elements, and because of that, change their properties. Like very popular in aircrafts is the aluminium copper alloy, which increase the strength of the material. There is also a lot of the whole spectrum of modification possibilities in case of magnesium alloys. The biggest one is elimination of its high flammability, which was a milestone for any application of this material. Due to magnesium and aluminium are one of the most active elements, they are very sensitive for corrosion. In the presence of alloying elements, this effect can be even accelerated because of formation of galvanic couples, where our metal will form the anodic side, be oxidized, and very quickly dissolve. Because of that, there is a big need to provide some efficient corrosion protection for those metals. The most popular and very effective type of anti-corrosion coatings were based on chromium-6. They were corrosion protection leaders since early 1920s, so in general from the moment of their invention. However, chromium-6 is very toxic and cancerogenic compound. Through respiratory tract, it can easily goes into the human body and damage the internal organs. Because of that, 18 years ago, European Commission decided to gradually limit the application of chromium-6 by establishing appropriate directives. They limit their application, and finally, in September 2017, the application of chromium-6 was completely forbidden. But replacing of older technology, which is well characterized, is not so easy, and because of that, for some crucial and critical application like aerospace, the application of chromium-6 is prolonged out until 2024. Our All Magic project, conducted in cooperation of our university, other scientific units like TU Delft from Netherlands, Helmholtz Centrum Gestadt, CIDAUT Foundation, and some companies like AkzoNobel, MTU, and Henkel, is focused on development of alternatives to chromium-6 coatings for aluminium and magnesium alloys. And it is dedicated exactly for advanced aerospace applications. Our main targets are to create safe and environmental friendly procedure of protection coating synthesis. At least they must be as good as chromium-6 coatings. And of course, they must be inexpensive and economically justified to have a real chance to be introduced into the industry. In the project, we are working on two types of coatings. Chemical conversion coatings, which are formed by chemical reaction, and anodic coatings, which are formed by electrochemical reaction. Those ones are, of course, cheaper in production, and this one required additional energy input, but shows better performance. This is the general mechanism of chemical conversion coatings formation. A part of the substrate is transformed into some insoluble phases in some appropriate pH, and it forms something which is more corrosion resistant and insoluble. The compounds that shows good corrosion performance can be in cations, anions, and organic species form. Currently, under the use is also the chromium-3 and vanadates, which will be soon forbidden also because of their toxic. They are also toxic. Chromium-3 is in detail not toxic by itself, but during the processing it turns to chromium-6. It might turn to chromium-6 compounds. Now, the big target in development of the coatings is introduction of active corrosion inhibitor species into the coating. In contrast to the base composition of the coating, we can introduce the inhibitors. The base coatings is responsible for the forming the protective layer from the environment, when the inhibitors are able to target specific region on the metal surface, interact with metal surface in corrosive media, and precipitate in form of some insoluble compound in the place of coating damage. Very novel is application of layered double hydroxide as a conversion coatings. It is composed of layer of 2+ and 3+ hydroxide and layer of anion mixture with water. This structure is so interesting because it can be loaded with corrosion inhibitors, and then in the presence of corrosive media, there is an exchange reaction that LDH bonds the chloride anion, and inhibitor is released and can be precipitated in the place of coating damage. The second big group of protective coatings are anodic oxide. They can be formed by a simple anodic reaction in the electrolyte, by application of external power source. The applied voltages can be very varied. We can do this procedure under two conditions, below breakdown potential and above breakdown potential, what provides different morphology of those coatings. Anodizing below breakdown potential is much better known techniques. Firstly, during this process, a thin oxide layer is formed, what corresponds to the current drop. Then, in the place of some imperfection of this layer, the pore starts form, what corresponds to the slightly increase of the current, and then the steady state formation of these long pores occurs, and it corresponds to this part of the current time curve. In this way, we obtain the very long porous structure with thin barrier layer very well attached to the metal surface. Second type of anodic coatings are coatings obtained by plasma electrolytic oxidation process, which is the process that required very high voltages applied. The beginning of the process is going through the same stages in the beginning, like the classic conventional anodizing. Firstly, some passive film is formed, then some porous structure, but after exceeding some breakdown voltage, the micro discharge and plasma formation starts. What is observed can be observed on the metal surface as formation of small sparks. Because of that, the plasma has very high temperature and pressure, and because of that, it can be through the discharge channel and form the layer on the surface. This way, obtain coating has 3 layers. Like the top layer is quite porous, but intermediate layer has a quite dense structure, and also there is a barrier layer without any pores. Also, it is worth to mention here that these techniques allow to a strong incorporation of elements from the electrolyte. Those two techniques, like conventional anodizing and PEO, have big difference. First of all, PEO required much higher powers. Second of all, the PEO used the dilute neutral or alkaline solution, and conventional anodizing used the acidic one. Big difference also is that using conventional anodizing in general, we cannot cover successfully the magnesium because of the peeling bedward ratio. This ratio defines the volume of oxide that is formed from some volume of metal. And in case of magnesium, it is lower than 1, what makes physically impossible to cover the magnesium by magnesium oxide. Also, there is a difference in corrosion mechanism. By the almost through-hole pores in conventional anodizing structure, the corrosive media can much easily appeal to the substrate. It is protected by this barrier layer. In case of PEO, we have some pores, but they are close both sides, so this process goes not so easy. Comparing the final results in a salt spray test, so under in corrosion fog, salt spray fog, we can see that aluminium protection obtained by classic anodizing can stand 1,000 hours, and in case of PEO, it is even 7,000 hours. Of course, this anodic coating can be improved by many options. Like, first of all, we can change some parameters that affect the basic part of the coatings, and for that we can change the anodic condition, like current and voltage. We can change the waveform parameters and duration of the process. Of course, the basic components of the electrolyte, or do some post-treatment sealing to reduce the porosity of these coatings. Second hand, we can improve long-time protection of our coatings by application of some active protection species, and we can use some in situ modifications by adding some small amount of some corrosion inhibitors into the electrolyte, as well as we can apply LDH as a post-treatment. The parameters of the process in case of classic anodizing, conventional anodizing, relates the thickness of the barrier layer with the potential. So by this is the relation. So by application higher voltages, we can obtain a thicker barrier layer, what is positive for anti-corrosion properties. However, in the same time, we will increase the dimension of the pore, which is bad effect for corrosion, anti-corrosion properties. So it's good to choose some optimal parameters that will be good in the both for the both thing. This relation is also used in some more advanced procedures, like by application of pulse procedure, pulse anodization, which provides the moderated size of the pores, and coatings like that can have better properties, like better hardness. Those are the electrolytes that are used typically for aluminium anodizing. They are acids. As I said before, the incorporation of electrolyte species in case of conventional anodizing is not so big as in case of PEO. The anions are introduced in the coating by simple migration in the electric field, so their distribution can be different through the depth of the oxide profile. Also, due to the mechanism of formation of this oxide, there are the regions that are free from these electrolyte species. We can modify the electrolyte by simple in situ doping, so by adding some small amount of some substances that can be in inorganic form or organic form and provide the corrosion inhibitors to the coating. Also, we can use particles which are very stable phases, like titanium oxide or zirconium oxide. Presence of these species also might affect the morphology of final coating. The last option is post-treatment pore sealing. As you can see, after very long time exposure for corrosive media, anodize, and the samples after anodizing and hydrothermal sealing, what is simple hot water treatment, looks much better than only anodized sample or even anodized with some chromium-6 post-treatment. To summarize, by application of varied acids for anodizing, varied modification of this procedure, like using in situ modification and post-treatments, we can obtain the coatings with different protection efficiency. The good news is that by only obtaining slightly thicker coatings like those one, we can get better corrosion protection than has the chromium acid anodizing. PEO coatings, we can use also similar strategy to modify the PEO coatings, like by application of different waveform. We can get different discharges during the process, what affect the final structure of the coating. Also, we can modify the composition of the electrolyte by using varied species. We can introduce to the coatings varied phases, and also it will affect the morphology of the final coating. There is also possibility to add some soluble species into the electrolyte. Then they can be organic or inorganic as well. By using some organic additives, we will affect mostly the PEO process, and this way we will change, for instance, gas evolution or discharge population density. And by introduction of some inorganic additives, we can introduce to the coatings more resistive species and some crystalline phases. Even if the morphology of these coatings is not so different, we can observe that presence of lanthanum or cerium improve the corrosion resistance of the coating. Electrolyte can be also modified by application of insoluble particles because the PEO is so high energetic process, then can be introduced into the coatings in the inert form or even in the reactive. So the new phases will be the effect of the reaction with the metallic substrate. Of course, because PEO is also a porous structure, we can use post-treatment sealing. So by application of some solutions or even chemical conversion treatments, we can reduce the porosity of the coatings, which very successfully reduce the corrosion current or moves the corrosion potential into higher values. One of the latest news is combining of the PEO treatments with these very successful conversion coatings, which is LDH. This is the picture of the PEO itself, and this is the combination of PEO with LDH. and by application also the corrosion inhibitors, we can significantly improve the corrosion protection. So to sum up, light alloys can have very wide application in transport due to their lower density. For this reason, we can reduce the fuel consumption and carbon dioxide production, but there is a big need to protect them from the corrosion. And the corrosion protection, since the chromium-6 coatings are prohibited, can be in form of chemical conversion coatings or an electrochemical anodizing or PEO. The advantage of chemical conversion coatings are low production cost, and in case of electrochemical anodizing or PEO coatings, it is higher corrosion protection. So this way, the level of protection can be adapted to the requirements. Thank you for your attention.
Thank you very much for a wonderful talk. And well, we have time for some questions if you want. No questions? Nobody? If you want to do it in Spanish, we can translate. No? Well, I think that this is very interesting results, and the question is, do you think that it's possible to transfer this technology to the companies in 5-10 years?
I'm sure that it is possible right now. We are working on it.
Yeah, oh, it's better. It's quite better. So that we can use better corrosion protections with lower environmental. Great. Congratulations for your work. Thank you very much. Well, thank you very much again. This is your home if you want to return in any moment. And I hope that you will have a lot of successful in your research in the future.
Thank you.
And see you again, sure.
See you.